And hello, we are back for some more statistical inferences. We're going to be looking at now the process for our hypotheses test. So last time we had defined a type 1 and a type 2 error and looked at the 4 scenarios that can occur and when we have conclusions that we make about accepting or rejecting the null hypothesis compared to the true state of the null hypothesis. And that arises into a type 1 error or a type 2 error. Type 1 error is when we reject a true null hypothesis, whereas the type 2 error comes about when we go about accepting a false null hypothesis. So when it comes to the hypotheses testing, once we've formed the null hypothesis and we've decided on the level of significance, okay, then we're going to now test the hypothesis using a test statistic. So the test statistic is given by this. This is similar to the z-score for normal distribution. So where our mean here, our sample mean, is what we're observing, whereas this here is the population mean. Okay, and here we're dividing by the standard deviation of the distribution of the sample mean. So this gives us a particular value on our standard normal curve, and what we're aiming to look at is, in fact, we're accepting the null hypothesis where our z numbers are in this region, about the mean. Whereas when we step over into this shaded region, which is the probability of the significance level, but half of it for a two-tailed test, then as soon as our test statistic z-score gives us a value in this region or this region, then that's the point where we reject the null hypothesis. Okay, so if it's less than or greater than some critical z value that corresponds to the level of significance, then the null hypothesis is rejected. Okay, let's consider this problem. So a manufacturer of a particular car tire uses a machine to study the wear and tear characteristics of tires. So the average tire tread is believed to last for about 17,000 kilometers with standard deviation of 1,500 kilometers. And a change in manufacturing is being considered. Okay, so here comes the intervention, which we're going to test with our hypothesis testing. So a sample of about 25 tires created with this new process was found to have a mean life of 17,400, which is a little bit more than what is considered as the population mean. So does this new process change the average mileage for the tire? What's going to be the conclusion overall? Okay, so first off, let's go about, from the information, identifying some key important values for our parameters and statistics. So the average tire tread is believed to last 17,000 kilometers. So that is what is our established average. That's our here population average, population mean. And it has a population standard deviation. So that's that amount there corresponding to this value. Then it speaks about a sample of 25 tires. So there's your sample size of 25. Okay, with a mean life of 17,400. There's the sample mean that we found from looking at the average of all the tire life of the 25 tires. Let's form our hypotheses. So the null hypothesis is where there's no change occurred. So the new process does not change the mileage for the new tires. So here is the mean is the same as the population mean, 17,000. So the alternative hypothesis is that this new manufacturing process does go about changing the average mileage for the tires. So the mean now is not equal to 17,000. So it's the exact opposite, mathematical opposite to the null hypotheses. Okay, Now, in this scenario, we're forming a two-tailed test because we haven't stipulated whether the new process is decreasing the average mileage for the tyres or increasing the average mileage for the tyres. It's just different. It's just a change is being observed. So we've got our significance level that we will set is spread across, is allotted to both tails. So we've got half of the significance here and half of the significance level here. Let's consider a significance level of 5%. So the area in the region of the two tails is 2.5% or 0.025. So using our inverse norm function on the CAS, that's going to correspond to this Z number, this critical Z number. So the minus 1.96 is down here and the positive 1.96 is up here. Now let's calculate our test statistic based on our sample mean and the standard deviation of our sample means. So there it is. There's a sample mean drawing on this value, x bar. Now that calculation gives us 1.33, which is less than 1.96. So what does that imply? Okay, so as the test statistic is less than the critical value, that leaves it in this region here, this light blue colored region, the main region. So that region there is where we fail to reject the null hypotheses. Okay, and we say that there is an insufficient evidence to reject this new process, that it does not change the mileage. So we have to go along and accept the assumption that we made in the beginning, that the null hypothesis is true, that there is no change. The new process does not change the mileage for the tyres. Get the idea? Alright. Now, there is another way we can do the same kind of hypothesis test. This way is looking at something called p-values. Now, p-value is the probability that is observed for obtaining a particular test statistic that is as extreme or more so than the value that we calculate. So if, say, the significance level corresponds to a critical Z value, Z star, which is this line, then the test statistic that we calculate gives us this value there. So greater than that test statistic, this blue region is what we call our p-value, our probability value. And it can be greater than that value, or it could be the reflection on the other side looking at this tail. It could be less than, in this case, the negative. Understand? Alright. So let's look at the same problem, but we're going to be considering the p-value in this case. So the first thing is, like we did before, identify what are the key pieces of information and find and summarize those parameters for our problem. Then we state our hypotheses. So again, as before, the null hypotheses, there is no change observed. So the mean is the 17,000 kilometers. Where the alternative hypotheses, we have that there is a change as observed, so it's not equal to 17,000 kilometers. Okay, so this identifies where mean is not equal to some amount. This identifies a two-tailed test. So for a 5% significance level, we get the area of the two tails are 0.025 respectively each. Okay, now from there we're going to determine our test statistic. And just like before in the previous example, that gave us a Z equals 1.33. So we don't need to find what is the critical Z number that corresponds to that area. Okay, because we're going to be determining the p-value, the probability value, and we're going to be comparing probabilities this time. We're not going to be comparing test statistic. We're not going to be comparing Z numbers. So now let's calculate what is our p-value for our z equals 1.33. Here it is. So determine the p-value. It is the probability that our z-score number is greater than or equal to this value. So that shows, can we find what is the chance of getting as a result that is as extreme or more so than what we observed. So we use the normal CDF function on the calculator for 1.33 as an improper fraction for 4/3, up to infinity for standard normal curve of mean 0 and standard deviation of 1, and we get this probability. So this is saying that now this amount is greater than the associated probability for the significance level. So it's not within, but it's on the outside of it. So what does that imply? Well, as the p-value 0.09 is greater than the probability for our significance level of 5%, then we fail to reject the null hypotheses. So there is insufficient evidence to reject that the new process does not change the mileage. Okay, so we have to result to the fact that we're accepting our assumption that the null hypothesis is true. Can everyone see the comparison between comparing our test statistic Z, whereas finding the p-value being a probability of that z-score number, that test statistic, using our normal CDF? Okay.